Hi, and welcome to the next video on better understanding the atomic structure. Today we're going to look at wave-particle duality. Now, this might be a slightly controversial theory on understanding what exactly happens around us. So before we begin, I'd like to say that particles and waves are constructs that we came up with to explain stuff we see, so some experimental results. So rather than focusing on the constructs themselves, we're going to take a look at what these results were and then follow from that and see why these interpretations came into play. So far we've seen that light is actually very interesting and can behave as an electromagnetic wave, which is what it popularly was known as, thinking of microwaves, for example. And it can also behave like a particle in the case of a photon. Similarly, some experiments on electrons suggested something very similar. So what they did was they took a source of electrons, so this guy produces electrons. They sent these electrons through what is known as a double slit experiment. So basically, the electron has two possible paths through which it can travel, and then they have a detector on the other side. And the detector, interestingly, gave a pattern that looks something like this. So the electrons didn't just go straight through and collide over there. The collisions of multiple electrons gave a specific pattern. So something light, dark, light, dark, light, so on and so forth, which looks something like a wave. Now this was known earlier to be an interference pattern, and it was observed when light is sent through these two slits. So when you have two waves that look something like this, and you superpose them, so you put the two waves in the same space, so if they occupy the same space, they are going to produce a resulting wave, which is a combination of both waves, which can look really like anything depending on how you combine these waves. And this phenomena where these waves combine is known as interference. So an easy way to understand this would be to look like what we considered waves to be classically. So originally, we considered waves to be a traveling disturbance in a medium. So if you think of ripples in water, what's really happening is that the water molecules are moving up and down and transmitting information to the neighboring water molecules. This is happening by the attraction between the two molecules. So let's say you have this water molecule. If this guy goes up, he's going to pull the water molecule next to him up. So he's going to pull this guy up, and he's going to pull this guy up. So if you track the movement of these particles and sort of draw it out, it's going to look something like this. And this is called a wave. Now, just as you see ripples traveling from one point to another, these waves travel. So the disturbances in the motion of the molecules. So at this point, this particle is going to come down, go up, and yeah, so the motion of these particles are in this axis, so in that direction, upwards and downwards, helps in the formation of a wave. Now, what do we mean when we're superposing a wave on this? Let's say you have another different type of motion of the particle, something that looks like this. What's going to happen is that this particle is going to want to move in a particular direction due to this wave, and it's going to want to move in the opposite direction due to this other wave. So as a net result, the particle isn't going to move. The same goes for this particle. So because of this wave, it wants to go upwards. Because of this wave, it wants to go downwards. And eventually, its position isn't going to change. So these two waves combine to give a net result of absolutely no movement, which is a type of interference known as destructive interference. Similarly, by applying this same analogy, we can see why if you superimpose two waves, for example, something like this, your result of the addition of these two, so this particle wants to go up that much, this one wants to go up a bit, it's going to go up in between. It's going to result in a pattern that may look something like that. So these are interference patterns, and we have explained it using disturbances in a medium such as water or air. However, when you come to electromagnetic radiation, there is no medium. However, wave behavior still applies, which is very interesting. So Maxwell found this, and interference behaves in the same way as it did within a medium, because light can travel through vacuum. Now, this interference pattern that is observed when light interacts, when light waves sort of merge together, was also observed when electrons were passed through the two slits. Now, electrons, since we thought they were particles, shouldn't have shown this interference, because interference is a characteristic of a wave, not a particle. Particle goes up, down, doesn't interact. It doesn't interfere with another particle in the way a wave does. And this led to de Broglie, a scientist, stating that matter has wave-particle duality, which means that particles can behave like waves, and waves can behave like particles. So we saw this in the case of electrons and photons, and this can be adapted to all matter. And he also stated that the wavelength of, well, a particle behaving like a wave can be correlated to the Planck's constant over the particle's momentum. Planck's constant over momentum. So you might ask, how would this make sense if you have large objects like a paper? So the wavelength of the paper, if we are interpreting it as a wave, would be Planck's constant, which is really small, over mass times velocity. Now the mass of this piece of paper is really large, and if we're moving it slowly, it has a high enough velocity. And because this value is so small, 6.626 into 10 power minus 34, the wavelength associated with this wave is very small. Because it's quite a big object. So you don't really see it as a wave. And this will make more sense when we look at what Heisenberg came up with. So Heisenberg is a really famous scientist who came up with an equation that looks something like this. So that is the reduced Planck's constant, is Planck's constant over 2 pi. That is uncertainty in position. That is uncertainty in momentum. Now he said that you can never exactly say both the position and the momentum with absolute precision, which means you'll have some error over here when you're measuring position, and you'll have an error while you're measuring momentum, and you cannot measure both of those to a precise point. Now this can be understood firstly in the context of de Broglie's waves, by seeing that a wave which is something like this sort of travels to infinity in both directions and doesn't have a position as such, because you can't say where the wave is because it just travels to infinity. But then if you add another wave that looks something like this, and keep adding a bunch of waves, you can come up with something that looks like this. And now you can say that the wave is in this position, because over here there's absolutely no disturbance. So what you're doing is you're localizing the wave, and you're creating a wave packet by adding up a bunch of waves together. Similar to how we got interference, in the same way multiple waves can interfere to give a wave that looks something like this, for example. So what you're essentially doing is you're reducing the uncertainty in X. I'm going to write this equation again. So if you're reducing this value, you would expect the uncertainty in momentum to go up according to this equation. And in fact, it does. That's because momentum can be correlated to wavelength, as we saw from de Broglie's equation, which means that now when you have infinite waves, you have infinite wavelengths, which means your uncertainty in momentum will go way up. So as soon as you start localizing the wave, you have to add up multiple wavelengths together, so your uncertainty in momentum goes up, and this equation sort of makes intuitive sense. Although Heisenberg came up with a different way to think about it. He said that if you want to look at the location of an electron, for example, you would have to send a photon. It will hit the electron, bounce off, you'll detect it, you can even time it. However, and you will get an idea of the position, relatively. However, the photon will also impart momentum, because it's two things colliding, and the momentum will go up. So if you're thinking about if I see this pen, I see that it's in one spot right there, and it has no momentum. That's because the uncertainty in momentum can be broken down to mass times uncertainty in velocity. And this is just a question of scaling. So this value right there, h bar over 2, is super small. And we don't even have ways of measuring the exact position of this pen down to the dot, like literally exactly where this pen is located. So delta x equals 0. That's not actually possible with any measurement devices we have. This value is in the order of 10 to the minus 34. So you can think about how small this value really is. If you think about the size of the pen, which in SI units would probably be, 0.1. So that's 10 to the minus 1 versus 10 to the minus 34. So since this value is super small, we don't actually see it when we're considering objects that are so big. However, if you're trying to look at objects that are really small, like electrons and protons, then this equation becomes really relevant. Now, Heisenberg's equation with de Broglie's wave-particle duality along with some experimental results led to the foundation of the Copenhagen interpretation and Schrödinger's equation. Now this is sort of historic in terms of theories of quantum mechanics, which aim to explain very small phenomena that could not be explained by considering the normal laws of physics, classical physics as we know it. And in subsequent videos, we're going to take a look at the Schrödinger equation, what it really says, and we're going to revisit the electron and photon double slit experiments to see if they actually behave like waves.